Welcome, class, and again we're going to be talking and dealing with chemical nomenclature and how to name, except today we're actually going to do the opposite. Instead of how to name chemical compounds, what we're going to actually do is kind of flip it around, and if you're given the name, how do you write the formula? And really, if you understand the naming process, then understanding how to write a formula is pretty easy. It's basically you're just going to flip-flop it around. The most difficult ones are your ionic bonds. Your covalent bonds are super simple. They're almost like freebies. Your ionic bonds are going to be a little more difficult because they don't use the Greek prefix system, and we'll deal with those in a minute here. We're going to start with covalent bonds. As you can see here, we have the names of a couple covalently bonded compounds, and you are going to need to identify as covalent or ionic when you not only go through the naming procedure, but also when you go through and are writing the formula. That will be important, and we'll see why. With covalent bonds, you're already going to have the Greek prefix system written there. So like this first one, trihydrogen phosphide. What that does for you is that makes your life really simple. Is the name tells you which elements you have, hydrogen and phosphide. Remember, we dropped the ending, added IDE, so that's phosphorus. So we have hydrogen and phosphorus bonded together. And the nice thing about covalent bonds is because we're using the Greek prefix system, then it tells us how many we're going to have. And remember, if there's nothing written in front, then we assume that it's one. It can either be mono or not written. So this first one here, I would have trihydrogen phosphide. I know that I have hydrogen. Here is my first element because it's written first. And the tri here tells me that there's three of them. So I'm going to write 3 for my first element. And then my second element is phosphorus here. So I'm going to write just a P. And there's only one of them. So this would be my correct formula. And I don't need to double check or use oxidation numbers or anything like that to try to see if I've got the correct formula, because my Greek prefixes tell me exactly how many I have. So it should be very simple when you have a covalent bond. And this would be your correct formula. That would be your answer to this if you were asked to write the formula given that name. And so let's look at our next one here. Again, it's a covalent bond. We know that for a couple reasons. One, you have nitrogen and sulfide or sulfur bonded together. Those are both nonmetals, so that would be a covalent bond. The other reason is we notice that it's using the Greek prefixes, so that would tell us that it's also a covalent bond as well. So we look at this and we notice that we have nitrogen and sulfur bonded together, so I know that my first element is going to be nitrogen. The question is how many, and this right here tells me how many I have. Di, well, if I know my Greek prefixes, that tells me I have 2 nitrogens. My next element is sulfide or sulfur. Okay, so I'm going to write an S, the chemical symbol for that. And then penta here tells me that I have 5 of them. And so I'm going to write 5, and there we go. I've got my formula. So I'm good to go on that there. So that would be how you do covalent bonds. There's not much to it because you're given and you're told what the individual elements are, and on top of that you're told how many you have. So that's pretty easy when it your next elements. Now what about if you have a situation similar to this? We have magnesium chloride. It's not a covalent bond, and again you could identify this. You have magnesium, which is a metal, chlorine, which is a nonmetal, and so that's an ionic bond. And so you know that you're not using your Greek prefixes. So how do I know what the formula is? Because I'm not told exactly how many I have. Well, this kind of goes back to why we learned oxidation numbers. This is where oxidation numbers are going to come in really handy. I do know this. I know I have magnesium, so Mg, and I know I have chlorine. So I know I have those two. What I don't know is how many of each do I have. Do I have 1 magnesium and 1 chlorine? Do I have 2 magnesiums and 1 chlorine? Do I have 2 chlorines and 1 magnesium? Or on and on we could go. So the way we figure this out is I do know this. I know that the sum of the oxidation numbers of the compound has to equal 0. And so as I've written the formula right now, is that actually the case? Well, what we can do is this. I know my oxidation number, and I'll write it down here below for this one. I know my oxidation number for magnesium is +2. How do I know that? Well, because it's an alkaline earth metal, and we know that all alkaline earth metals are always +2 when they're bonded. That's its oxidation number. I also know that chlorine has an oxidation number of -1 because it's a halogen. Halogens, whenever they're bonded to metals, are always -1. Okay, so as I look here, does this add up to 0? Well, no, it doesn't. So I don't have the correct formula. I have the right elements, but not the right amounts. So what I need to do is adjust this to find, what's my correct amounts. And it's real easy to do. Basically, what I'm going to do is find my least common multiple. In other words, what will they both, or what could they both multiply into? In this case, it would be 2. So I don't need to change magnesium. I do need to change chlorine. I need 2 chlorines in order to equal everything out. If we wanted to look at it in terms of our equation here, I want it to equal 0. Magnesium is 2 plus I have chlorine, which is -1. In order to make it 0, I would need 2 chlorines. So I could look at it that way, and if that's true, then I would need 2 Cl's here, and that would be my correct formula, MgCl2. Okay, that's kind of how that would work. So let's look at it in another way as well. So let's look at sodium oxide here. So we know that we have sodium, and we know that we have oxygen together. The question is, how many sodiums, how many oxygens? I don't know each one, but I do know that sodium has an oxidation number of +1. How do I know that? Again, the oxidation number rules that you guys learned told us that sodium, it's an alkali metal, and so it always has an oxidation number of +1. Oxygen, we learned, has an oxidation number of -2. And so as I look at these, do they add up to 0? No, they don't. And so what's kind of the least common multiple between these two? It's 2. And so I need them to equal out to 0. Well, if they're going to equal out to 0, if I'm going to have a sum of 0, I have +1 here in sodium plus -2 over here. This obviously doesn't equal out to 0 there as it's written. What I would need to do is have 2 of these here for the thing to equal out. Well, okay, that means I have to have 2 sodiums, right? And so there, I've got my formula written correctly now. Now I have 2 sodiums to 1 oxygen. Sometimes it may be 3 or 4, or it may be a ratio of 2 to 3, depending. But you have to use your oxidation numbers to find out what the correct formula is. If I don't do that, then I'm going to end up getting it incorrect. All right, what about if you have a ionic bond using a transition metal or a metal or post-transition metal that has more than one oxidation state? So for example, manganese here, which has multiple oxidation states, and so we've got the name using the stock system or the Roman numeral system there with manganese 4 bromide. So I know right off the top that I have my 2 elements or 2 compounds. I have manganese and I have bromine here. So I have those 2. What I don't know on each of these is how much of each do I have. I don't know that. So what I'm going to do is I use my oxidation numbers. Now the cool thing is I'm already told what my oxidation number of manganese is. Where am I told that? Right here. Remember, that's what the Roman numeral tells us. Okay, we learned that earlier when we were talking about the naming procedure. That's what that Roman numeral tells me. It tells me the oxidation number of manganese. Okay, so that's 4. That's the Roman numeral 4. So I know that manganese, my metal, has an oxidation number of 4. Bromine is a halogen. It has an oxidation number of -1. So what's my least common multiple between these two? It's 4. And so if I wanted to set up an equation and try to figure, well, the whole thing has to equal 0, I have manganese, which is 4, plus bromine, and bromine is -1. Obviously, that doesn't add up to 0. So what would I need to change? Well, I would need 4 bromines, okay, in order to equal 0. So that's what I'm going to change here. So my actual formula would be MnBr4. It would be how it's written. So that's how we do that. Let's take a look at another one. And this one we have copper 2 sulfide, and this will be the last one we look at, and then we'll do lots of practice with these as we go in class. And again, this is an ionic bond. You'll notice we're spending more time with the ionic bonds, and the reason we're spending more time with the ionic bonds, quite simply, is because they're a little more difficult because you have to use the oxidation numbers with them. So I have copper, and sulfide is sulfur, and so we have copper, which is Cu, and I have sulfur, which is S here, and the question is, okay, well, what's the relationship between them? Is this the correct formula, or do I need 2 coppers or 3 coppers, or do I need 2 sulfurs or 3 sulfurs or 4 sulfurs, or what? Or is there a ratio between them? I need to figure that out. Well, I do know copper's oxidation number is +2, and I know that sulfur's oxidation number, I can figure it out because it is an ionic bond. It's an ion. It has 6 valence electrons, so it's going to gain 2, meaning it's going to have a charge of -2 if it gains 2 electrons. If it has a charge of -2, we learned that whatever the charge is, that will also be its oxidation number. So it's -2. So as I look at these, well, this is kind of handy because in this case, I have a +2 on this side of my metal and a -2 on this side. And so what I end up with is that it equals 0 already. So guess what? I don't need to do anything to this one. This formula is already correct. And in some cases, that's what you'll end up with, is a formula that it's already written correctly as you begin. But you have to double check because you don't know right off the top of your head. A lot of times you're going to have to adjust something in an ionic bond, either the metal or the nonmetal, or sometimes both. You will have to adjust. So that's basically how you write a formula. You're just going to reverse everything around from the naming procedure. And so if you understood the naming procedure, then it shouldn't be super difficult to turn around and write the formulas from it. And again, we're going to do a lot of practice with that in class.